right now, somewhere between Mars and Jupiter, there is a region of space so misunderstood that almost everything you think you know about it is wrong. You have seen it in movies. You have seen it in video games. A terrifying wall of tumbling rocks, smashing into each other, destroying anything that dares to fly through. But what if I told you that the real asteroid belt is nothing like that? What if the truth is far stranger, far quieter, and far more unsettling than any Hollywood scene could ever dream up? That is exactly what we are going to explore tonight. Because the story of the asteroid belt is not just a story about rocks floating in space. It is a story about a planet that never got the chance to be born. A story about a bully so massive it warped the fabric of space itself. And a story about how that ancient act of cosmic violence may have been the single most important event in the history of life on Earth. So settle in, get comfortable, and let me take you on a journey to one of the most misunderstood places in our entire solar system. To understand the asteroid belt, we first need to understand where it lives. Picture our solar system like a giant neighborhood. The sun sits right in the center, like a glowing street light that never turns off. Closest to that light, you have the small rocky worlds: Mercury, Venus, Earth, and Mars. These are the inner planets, the ones made of rock and metal, the ones that feel the warmth of the sun on their surfaces every single day. Then, much further out, you have the gas giants: Jupiter, Saturn, Uranus, and Neptune. These are the heavyweights, the outer planets. Massive balls of gas and ice that dwarf everything else in the neighborhood. Now, between those two groups, between Mars and the first gas giant Jupiter, there is a gap, a vast, yawning gap of space that stretches for hundreds of millions of miles. And it is inside this gap that the asteroid belt lives. Think of it like a ring of debris circling the sun. Millions of chunks of rock and metal, all orbiting in a wide band between the fourth and fifth planets. Some of these chunks are tiny, smaller than a grain of sand. Others are enormous. Some are hundreds of miles across, large enough to be considered small worlds in their own right. The biggest object in the asteroid belt is called Ceres, and Ceres is so large that scientists actually classify it as a dwarf planet. It is roughly 590 miles across. To put that in perspective, that is about the distance from Los Angeles to San Francisco. Imagine a single rock that wide, just floating out there in the darkness between Mars and Jupiter. Ceres alone makes up about a third of the total mass of the entire asteroid belt. It is the king of that region, the biggest fish in a very, very large pond. But here is where the first big misconception comes in. When most people picture the asteroid belt, they imagine something like a dense cloud of rocks, a minefield, a place where asteroids are packed so tightly together that you would have to dodge and weave just to get through. Every science fiction movie has trained us to think this way. The hero pilots the ship into the asteroid belt, and suddenly rocks are flying everywhere, smashing into each other, creating explosions and chaos. The reality could not be more different. The asteroid belt is almost entirely empty space. The distances between individual asteroids are enormous. We are talking millions of miles between one rock and the next. If you were standing on one asteroid in the belt and you looked around, you would not see any other asteroids. Not a single one. They would all be too far away to see with the naked eye. The belt would look like nothing but black, empty space stretching out in every direction. In fact, NASA has sent multiple spacecraft straight through the asteroid belt, and not a single one has ever had a close call with an asteroid. Not once. The spacecraft just cruised right through without any issues at all. The odds of hitting an asteroid while passing through the belt are astronomically low. Some scientists have estimated that the chance is roughly 1 in a billion. You are more likely to win the lottery multiple times in a row than you are to accidentally bump into a rock while flying through the asteroid belt. So why do the movies get it so wrong? Well, because the truth is not very dramatic, is it? A vast, silent, empty stretch of space does not exactly make for an exciting action scene. But that emptiness, that silence, is actually one of the most fascinating things about the belt, because it raises a question that scientists have been wrestling with for centuries. If the asteroid belt sits in this huge gap between Mars and Jupiter, and if it contains millions of rocky objects, then why is it so empty? Why is there not more stuff out there? And more importantly, why is there not a planet there? Think about it. Everywhere else in the solar system, matter came together to form planets. Closer to the Sun, the rocky material clumped together to make Mercury, Venus, Earth, and Mars. Further out, gas and ice gathered into Jupiter, Saturn, Uranus, and Neptune. But right there in the middle, in this massive gap between Mars and Jupiter, the material just never came together. It never formed a planet. Instead, it remained scattered in millions of pieces, like a jigsaw puzzle that was never assembled. And the reason for that is one of the most dramatic stories in all of planetary science. To understand why the asteroid belt exists, we need to go back in time, way back. About 4.5 billion years ago, our solar system was just being born. The sun had recently ignited, a brand new star burning bright for the very first time. And surrounding it was a massive disk of gas, dust, and debris. This disk is called the protoplanetary disk, and it was the raw material from which everything in our solar system would eventually be built. Every planet, every moon, every comet, every asteroid, it all came from this spinning disk of cosmic stuff. Now, within this disk, something incredible was happening. Tiny grains of dust were bumping into each other and sticking together. Over time, those clumps grew bigger, and bigger, and bigger still. This process is called accretion, and it is how planets are born. Small pieces come together to form larger pieces, which come together to form even larger pieces, until eventually you have objects big enough to be called planetesimals. These are the building blocks of planets. Rocky bodies ranging from a few feet across to several miles wide, all swirling around the young sun, all crashing into each other and growing with every collision. In most regions of the protoplanetary disk, this process worked beautifully. The planetesimals merged and grew and eventually became the planets we know today. But in the region between Mars and Jupiter, something went terribly wrong. The planetesimals started to come together, just like they did everywhere else. They were on their way to forming a planet, a fifth rocky world that would have sat right between Mars and the gas giants. Scientists sometimes call this hypothetical world Planet 5, or sometimes they refer to the idea as the missing planet. But this planet never got the chance to form, and the reason is Jupiter. Jupiter is a monster. There is simply no other way to describe it. It is the largest planet in our solar system by a ridiculous margin. You could fit over 1/300 Earths inside Jupiter and still have room to spare. Its mass is more than twice the mass of all the other planets in the solar system combined. And all that mass means one thing: gravity. Incredibly powerful gravity. Jupiter's gravitational pull is so strong that it reaches out across millions of miles of space and influences everything around it. And 4.5 billion years ago, as the planets were still forming, Jupiter's gravity reached into the region where the asteroid belt now sits and caused absolute chaos. See, for a planet to form, the planetesimals in a region need to come together gently. They need to collide at relatively low speeds so they can stick together and grow. But Jupiter's gravity stirred up the planetesimals in the belt region like a giant spoon stirring a pot of soup. It increased their speeds. It made their orbits more elliptical, more stretched out, more chaotic. And when objects are moving that fast and on such wild orbits, they do not gently come together. They smash into each other violently, and instead of building up, they break apart. This is what happened in the asteroid belt. Jupiter's gravity turned what should have been a calm construction zone into a demolition derby. The planetesimals could not come together to form a planet because every time they tried, Jupiter's influence would speed them up and send them crashing into each other at destructive speeds. Instead of growing, they shattered. Instead of building, they broke. And over millions of years, the material in that region was ground down from potential planet-sized bodies into the millions of smaller fragments we see today. It is a tragic story when you think about it. There was a planet trying to be born out there. The raw materials were in place. The process had begun, but it was bullied into oblivion by the biggest kid on the block. Jupiter robbed that region of its future. It prevented a world from coming into existence. And what we see today in the asteroid belt is not a collection of debris from a planet that exploded. That is another common misconception. The asteroids are not the broken remains of a destroyed world. They are the unassembled pieces of a world that was never allowed to exist in the first place. There is something deeply poignant about that. Imagine a house that was never built. The bricks are all there, scattered across the lot. The foundation was started but never finished. The blueprints existed. The potential was real. But something came along and made sure it could never be completed. That is the asteroid belt, a cosmic construction site that was abandoned before the work could be done. And those scattered bricks, those leftover pieces, have been orbiting the Sun in lonely silence for 4.5 billion years, waiting for a construction crew that will never return. Now, when I say that Jupiter prevented a planet from forming, I want to make sure we understand the scale of what was lost, because the asteroid belt, despite containing millions of objects, is actually not very massive at all. If you took every single asteroid in the belt and combined them all into one object, the total mass would be surprisingly small. The entire asteroid belt has a mass of roughly 4% of our Moon. Let me say that again, because it is worth letting that sink in. All of those millions of asteroids, all of that debris scattered across hundreds of millions of miles of space, adds up to less than 4% of the mass of our Moon. Our Moon, which is already a tiny object compared to Earth. So, what happened to all the material that was originally in that region? If the asteroid belt is so light, where did everything go? The answer, once again, is Jupiter. Not only did Jupiter prevent a planet from forming, but over billions of years, its gravity actually ejected most of the material out of the belt entirely. Jupiter flung rocks inward toward the Sun, outward into the far reaches of the solar system, or absorbed them into itself. Scientists estimate that the asteroid belt once contained many times more mass than it does today. Some estimates suggest it may have once held the equivalent of several Earth masses worth of material, but Jupiter stripped it away, piece by piece, over billions of years, until only a tiny fraction remained. Think about that for a moment. The asteroid belt we see today is just the leftovers of the leftovers, a pale shadow of what once existed in that region. It is like finding a few crumbs on a plate and trying to imagine the feast that was once there. The vast majority of the original material is gone, scattered to the cosmic winds by Jupiter's relentless gravitational influence. And yet, even in its diminished state, the asteroid belt is a treasure trove of scientific information, because those remaining asteroids are some of the oldest objects in the solar system. They are fossils, time capsules from the very earliest days of our cosmic neighborhood. While the planets have been changed and transformed over billions of years by volcanism, plate tectonics, weather, and other processes, many of the asteroids in the belt have remained virtually unchanged since they first formed 4.5 billion years ago. They are pristine samples of the original building material of the solar system. Studying these asteroids is like reading the diary of the solar system's childhood. They can tell us what conditions were like in the protoplanetary disk. They can tell us about the composition of the original material that went on to form the planets. They can tell us about the temperatures, pressures, and chemical processes that were at work during those earliest days. In many ways, the asteroids know more about our origins than the planets themselves do, because the planets have been so thoroughly transformed that much of their original character has been erased. The asteroids, on the other hand, remember. This is why space agencies around the world have been so eager to visit asteroids and bring samples back to Earth. NASA's OSIRIS-REx mission traveled to an asteroid called Bennu, collected samples from its surface, and brought them back to Earth in 2023. Japan's Hayabusa 2 mission did the same thing with an asteroid called Ryugu. These missions are not just about studying rocks. They are about unlocking the secrets of our own origins, because we are all made of the same stuff that those asteroids are made of. The carbon in our bodies, the iron in our blood, the calcium in our bones, it all came from the same cloud of material that formed the asteroids 4.5 billion years ago. When we study an asteroid, we are in a very real sense studying ourselves. But let us go deeper into the belt itself, because it is not just one uniform collection of similar rocks. The asteroid belt is actually a surprisingly diverse place, with different types of asteroids that tell very different stories about the conditions in which they formed. Scientists generally classify asteroids into 3 main types based on their composition. The first, and most common type, is called C-type, or carbonaceous asteroids. These are the dark ones. They do not reflect much sunlight, which makes them hard to spot from Earth. C-type asteroids are rich in carbon and organic compounds, and they are thought to be the most primitive objects in the belt. They have changed very little since the solar system's earliest days, making them incredibly valuable for scientific study. About 75% of all known asteroids fall into this category. The second type is called S-type, or silicaceous asteroids. These are made primarily of silicate minerals and nickel iron. They are brighter than C-type asteroids and are the second most common type in the belt. S-type asteroids are found mostly in the inner part of the belt, closer to Mars, and they tell us about the rockier, more metal-like conditions that existed closer to the Sun during the solar system's formation. The third type is called M-type, or metallic asteroids. These are the fascinating ones. M-type asteroids are made almost entirely of metal, primarily nickel and iron. Scientists believe that many of these metallic asteroids are actually the exposed cores of larger bodies that were destroyed in ancient collisions. Think about that for a second. When a large planetesimal forms, its interior separates into layers, just like Earth did. Heavy metals sink to the core, while lighter rocky material floats to the surface. If that planetesimal is then smashed apart by a violent collision, the rocky outer layers are blasted away, but the dense metallic core can survive as a separate object. That is what M-type asteroids are. They are the beating hearts of dead worlds, the cores of bodies that were torn apart billions of years ago, and they are just floating out there in the darkness, exposed and naked, their secrets visible for anyone who cares to look. One particular M-type asteroid has captured the imagination of scientists and the public alike. It is called 16 Psyche, and it is one of the most extraordinary objects in the entire solar system. Psyche is roughly 140 miles across, making it one of the larger asteroids in the belt. But what makes it special is not its size. It is what it is made of. Psyche appears to be almost entirely metal, a massive chunk of nickel and iron floating through space. Scientists believe it may be the exposed core of a protoplanet that was stripped of its outer layers by catastrophic collisions early in the solar system's history. The amount of metal in Psyche is staggering. Some early estimates suggested that if you could somehow mine all the metal in Psyche and bring it back to Earth, it would be worth something like $10 quintillion. That is a 10 followed by 18 zeros. Enough money to make every single person on Earth a billionaire many times over. Now, those numbers should be taken with a grain of salt, because flooding the market with that much metal would obviously crash the value. But the point stands. Psyche contains an almost unimaginable quantity of valuable metals. NASA was so intrigued by Psyche that they launched a dedicated mission to study it. The Psyche spacecraft launched in October 2023 and is currently on its way to the asteroid. It is expected to arrive in 2029, and when it does, it will be the first time humanity has ever visited a metallic asteroid. The mission will help scientists understand what the cores of rocky planets are like, since we cannot directly study Earth's core. Psyche gives us a chance to see a planetary core up close, exposed and accessible in a way that would be impossible on any living planet. The spacecraft is equipped with a suite of scientific instruments designed to map Psyche's surface, measure its gravity field, and determine its composition. One of the most exciting instruments is a gamma-ray and neutron spectrometer, which will identify the elements present on the asteroid's surface by measuring the radiation they emit when struck by cosmic rays. Another instrument is a magnetometer that will search for evidence of a remnant magnetic field, which would confirm that Psyche was once the molten core of a larger body that generated its own magnetic dynamo, similar to how Earth's liquid iron core generates our planet's magnetic field today. If Psyche does have a remnant magnetic field, it would be extraordinary evidence of a world that once had a beating heart of molten metal, generating invisible lines of magnetic force that reached out into space. A world that was alive, in a geological sense, with a dynamic interior that churned and flowed and created a magnetic shield against the radiation of space. And then that world was destroyed, its outer layers stripped away, its core exposed to the void, frozen and silent. The remnant magnetic field would be like a ghost, a faint echo of the living world that once was. But Psyche is just one object among millions. The asteroid belt contains an incredible variety of worlds in miniature. Some asteroids are solid chunks of rock or metal. Others are loose piles of rubble held together by nothing more than their own weak gravity. These are called rubble pile asteroids, and they are exactly what they sound like. Collections of smaller rocks and boulders that are gravitationally bound to each other but not fused together. If you could reach out and push on a rubble pile asteroid, it might actually shift and deform under your touch, like pushing on a pile of gravel. The asteroid Bennu, the one that NASA's OSIRIS-REx mission visited, turned out to be a rubble pile. When the spacecraft arrived and got its first close-up look, scientists were surprised to find that Bennu's surface was covered in boulders and loose rocks, with very little fine-grained material between them. It looked like a pile of gravel floating in space. And when the spacecraft attempted to collect a sample by touching the surface briefly, it sank into the asteroid much more than expected, suggesting that the surface was loosely packed and not very dense. This discovery was important because it changed our understanding of how we might deal with a potentially dangerous asteroid heading toward Earth. If a rubble pile asteroid were on a collision course with our planet, you could not just hit it with a missile and expect it to be deflected. The loose structure would absorb the impact like a pillow absorbing a punch. You would need a completely different strategy. This is one of the many reasons why studying asteroids is not just academic curiosity. It could one day be a matter of survival for our entire species. Speaking of dangerous asteroids, let us talk about what happens when rocks from the asteroid belt do head our way. Because while the belt itself is far from Earth, it is not a perfectly stable place. Jupiter's gravity is constantly tugging on the asteroids, shifting their orbits, occasionally sending them on new paths. And sometimes, those new paths bring them closer to the inner solar system, closer to us. There are specific regions within the asteroid belt where asteroids are noticeably absent. These empty zones are called Kirkwood gaps, named after the American astronomer Daniel Kirkwood, who first noticed them back in 1866. Kirkwood was studying the orbits of asteroids, and he realized that at certain distances from the Sun, there were almost no asteroids at all. These gaps correspond to orbital resonances with Jupiter. Now, what is an orbital resonance? It is actually a beautifully simple concept. Imagine you are pushing a child on a swing. If you push at just the right moment, in sync with the swing's natural rhythm, the swing goes higher and higher with each push. You are adding energy at just the right time. That is essentially what Jupiter does to asteroids at certain orbital distances. If an asteroid orbits the Sun at a distance where it completes exactly 2 orbits for every 1 orbit Jupiter completes, or 3 orbits for every 1, or some other simple ratio, then Jupiter's gravitational pull hits that asteroid at the same point in its orbit over and over again. Each time, Jupiter gives it a little tug, and over millions of years, those tiny tugs add up, gradually changing the asteroid's orbit until it is flung out of that region entirely. It is like Jupiter is reaching into the belt with invisible fingers and plucking out any asteroid that happens to wander into one of these resonant zones. The result is a series of clean gaps in the belt, empty corridors, where no asteroid can remain for long. These Kirkwood gaps are visible evidence of Jupiter's ongoing influence on the belt. They are scars carved into the distribution of asteroids by the gravitational power of the solar system's largest planet, and they have been there for billions of years, silently, maintained by the same force that prevented the belt from becoming a planet in the first place. But Jupiter's influence on the belt is not just about destruction and prevention. In a strange twist, Jupiter's gravity also helps to keep the asteroid belt somewhat organized. Without Jupiter, the asteroids would be far more spread out, their orbits more chaotic, their interactions more unpredictable. Jupiter acts like a shepherd, corralling the asteroids into a relatively defined band. It prevents them from scattering too far inward or too far outward. In a sense, Jupiter both created the asteroid belt and maintains it. It is both the destroyer and the caretaker of that region. This dual role is one of the most fascinating aspects of Jupiter's relationship with the belt. The same force that prevented a planet from forming also ensures that, The remaining debris stays in a relatively orderly band around the Sun. It is like a bully who beats up a kid and then makes sure nobody else bothers them. A strange kind of protection that arises from the same source as the original harm. Now, I mentioned earlier that the asteroid belt is astonishingly empty. But I want to take a moment to really drive that point home, because it is one of those facts that is so counterintuitive that your brain almost refuses to accept it. The total volume of space occupied by the asteroid belt is enormous. If you think of it as a donut-shaped ring around the Sun, that ring is roughly 200 million miles wide, measured from its inner edge near Mars to its outer edge approaching Jupiter. The circumference of the belt, the distance all the way around, is billions of miles. The total volume of space within the belt is beyond comprehension. And within that incomprehensibly vast space, the total amount of solid material is tiny. If you could gather up every single asteroid in the belt, every rock, every pebble, every grain of dust, and combine them all into one object, that object would be smaller than our moon, significantly smaller. The entire asteroid belt has less than 4% of the moon's mass, so we are talking about a tiny amount of material spread across an unfathomably large volume of space. The average distance between asteroids in the belt is something like 2 to 3 million miles. That is roughly 10 times the distance between the Earth and the Moon. So if you were standing on one asteroid and looking toward the next closest one, it would be 10 times further away than the Moon appears in our sky. And since asteroids are much, much smaller than the Moon, you would have absolutely no hope of seeing it. It would be a tiny speck, invisible against the blackness of space. This is why I call it the void paradox. We call it a belt, which implies a continuous band of material. But in reality, it is more like a very, very sparse scattering of lonely rocks, each one separated from its nearest neighbor by a gulf of emptiness that is hard to even conceptualize. The belt is defined more by the space between the asteroids than by the asteroids themselves. It is a region of almost nothing, with occasional tiny somethings floating through it at vast distances from each other. If you were an astronaut flying through the asteroid belt, your experience would be profoundly boring from a visual standpoint. You would not see rocks tumbling past your window. You would not need to dodge or weave. You would see nothing but stars and blackness, the same view you would have in any other part of deep space. The asteroid belt would be completely indistinguishable from the empty void between the planets. The only way you would even know you were in the belt would be if your instruments told you so. Your eyes would see nothing different at all. And there is something almost eerie about that. Here is this region of space that we have given a name to, that we have classified as a distinct feature of our solar system. And yet, if you were actually there, floating in the middle of it, you would have no idea. It would look and feel exactly like nothing. The same infinite darkness in every direction. The same pinpricks of distant starlight. The same crushing absolute silence that defines all of space. The asteroid belt is, in the most literal sense, almost nothing. But that almost is everything, because those rare scattered rocks contain within them the story of how our solar system was built. Each asteroid is a chapter in a book that spans billions of years, and together they tell a story that is far more dramatic, far more violent, and far more beautiful than most people realize. Let us talk about what those asteroids are actually like up close, because while we tend to think of them as boring grey rocks, the reality is much more interesting. Asteroids come in an astonishing variety of shapes, sizes, colors, and compositions. Some are round, smoothed by their own gravity into rough spheres. Others are wildly irregular, shaped like potatoes, dumbbells, dog bones, or even rubber ducks. The asteroid Itokawa, which was visited by Japan's first Hayabusa mission, looks remarkably like a sea otter floating on its back. The asteroid Cleopatra looks like a giant metallic dog bone. These strange shapes are the result of billions of years of collisions, fragmentation, and gravitational interaction. Some asteroids even have their own moons. That is right, tiny worlds orbiting other tiny worlds. The first asteroid moon was discovered in 1993, when the Galileo spacecraft, on its way to Jupiter, passed close to an asteroid called Ida and spotted a tiny companion orbiting around it. This little moon was named Dactyl, and it is only about a mile across. Since then, scientists have discovered that many asteroids have moons, and some even have two. The asteroid Sylvia, for example, has two tiny moons orbiting it, named Romulus and Remus. The existence of asteroid moons tells us something important about the violent history of the belt. Most of these moons are thought to be fragments that were knocked off the main asteroid by a collision and then captured by its gravity. So each asteroid with a moon is carrying around physical evidence of an ancient impact, a piece of itself that was blasted off and then gently pulled back into orbit. It is like wearing a scar as a piece of jewelry. And then there are the binary asteroids. These are pairs of asteroids that orbit around each other, locked in a gravitational dance that can last for billions of years. Sometimes the two objects are roughly the same size, making it hard to say which one is the asteroid and which is the moon. They just spin around each other, endlessly circling a point between them, like two dancers holding hands and twirling on an empty dance floor. It is one of the most elegant phenomena in the solar system, and it plays out in absolute silence, witnessed by no one, in the vast emptiness between Mars and Jupiter. Now, let us turn our attention to some of the specific asteroids that have taught us the most about this fascinating region. I already mentioned Ceres, the largest object in the belt, but Ceres deserves a much deeper look because it is truly extraordinary. Ceres was actually the first asteroid ever discovered. It was found on January 1st, 1801, by the Italian astronomer Giuseppe Piazzi. Piazzi was surveying the night sky from his observatory in Sicily when he spotted a point of light that moved against the background stars. At first, he thought it might be a comet, but it did not have a tail, and its motion suggested it was orbiting the Sun in a nearly circular path. Over the following weeks, other astronomers confirmed his observation, and it became clear that Piazzi had found something new: a small world orbiting the Sun between Mars and Jupiter. Ceres was initially classified as a planet. For nearly 50 years, it appeared in astronomy textbooks as the 8th planet in our solar system. But as more and more objects were discovered in the same region, scientists realized that Ceres was just the largest member of a vast population of small bodies, and it was reclassified as an asteroid. Then, in 2006, the same year that Pluto was famously demoted from planet status, Ceres was promoted to dwarf planet. So Ceres has had quite the journey through our classification system. Planet, then asteroid, then dwarf planet. It has been labelled and relabelled as our understanding of the solar system has evolved. But what makes Ceres truly fascinating is what NASA's Dawn mission discovered when it arrived there in 2015. Dawn was the first spacecraft to orbit a dwarf planet, and its observations of Ceres were full of surprises. The most dramatic discovery was the bright spots in Ocata crater. When Dawn's cameras first captured images of this crater, scientists noticed intensely bright patches on the crater floor, that stood out dramatically against the dark surrounding surface. These bright spots sparked intense debate and speculation. What could they be? After careful analysis, scientists determined that the bright spots were deposits of sodium carbonate, a type of salt. And this salt appeared to have been brought to the surface by liquid water that had welled up from beneath the crust. This was a stunning revelation. It suggested that Ceres has, or recently had, a subsurface ocean. Liquid water hiding beneath its icy crust, occasionally finding its way to the surface and leaving behind these bright salt deposits as it evaporated into space. The idea that a small body in the asteroid belt could harbor liquid water was a game changer. Water is one of the key ingredients for life as we know it. And if Ceres has water beneath its surface, then it joins a growing list of worlds in our solar system that might, just might, have the conditions necessary to support some form of life. We are not talking about aliens walking around on Ceres, but simple, microscopic organisms living in a dark, salty ocean beneath the surface. It is not impossible. And that fact alone makes Ceres one of the most intriguing objects in the entire solar system. Dawn also discovered that Ceres has a mountain called Ahuna Mons that is genuinely bizarre. It rises about 3 miles from the surrounding terrain, making it one of the tallest features on Ceres. But what makes it strange is that it appears to be a cryovolcano, a volcano that erupts not with molten rock, but with ice, water, and other volatile materials. The idea of a volcano made of ice sounds like something out of a fantasy novel, but it is very real. On worlds far from the sun, where temperatures are cold enough, water can behave the way lava behaves on Earth. It can well up from beneath the surface, flow across the landscape, and build up into mountain-like structures. Ahuna Mons appears to be relatively young by geological standards, perhaps only a couple 100 million years old, on a body that is 4.5 billion years old. That is practically yesterday. This suggests that Ceres may still be geologically active in some way, that processes beneath its surface are still at work even now, slowly reshaping this small world in the frigid darkness of the asteroid belt. Ceres also has a thin atmosphere. Though calling it an atmosphere is perhaps generous, it is more of an exosphere, an incredibly tenuous shell of water vapor that clings to the surface. This water vapor is thought to come from ice on the surface that sublimates, meaning it transitions directly from solid ice to gas when it is warmed by sunlight. The existence of this water vapor further supports the idea that water is an important part of Ceres's makeup, both on the surface and potentially deep beneath it. Let me pause here for a moment and let all of this sink in. We are talking about an object in the asteroid belt, a region that most people think of as nothing but lifeless rocks floating in a void, and yet this object has a subsurface ocean, ice volcanoes, an atmosphere of water vapor, and bright salt deposits on its surface. Ceres is a world, a small one, a cold one, a dark one, but a world nonetheless. And it is hiding extraordinary secrets in the most unlikely of places. But Ceres is not the only asteroid that has surprised us. Let me tell you about Vesta, the second largest object in the belt, and another target of the Dawn mission. Vesta is about 326 miles across, making it significantly smaller than Ceres, but still a substantial body. And Vesta has its own remarkable story to tell. The most striking feature of Vesta is a massive impact basin near its south pole called Rhea Silvia. This crater is about 310 miles across, which means it spans nearly the entire diameter of Vesta itself. The impact that created Rhea Silvia was so powerful that it blasted away roughly 1% of Vesta's total volume, sending enormous chunks of rock flying off into space. Many of these chunks are still out there, forming their own family of smaller asteroids that share similar orbits and compositions. Scientists call them the Vesta family, or Vestoids. But here is the truly remarkable part. Some of those chunks made it all the way to Earth. There is a specific type of meteorite called an head meteorite, which stands for Howardites, Eucrits, and Diogenites. These meteorites have chemical compositions that closely match the surface and interior of Vesta. Scientists believe they are literally pieces of Vesta that were blasted off by the Rhea Silvia impact and eventually found their way to Earth's surface. So if you have ever seen an head meteorite in a museum, you are looking at a piece of the asteroid belt, a fragment of Vesta that traveled millions of miles through space before falling through our atmosphere and landing on our planet. Think about that connection for a moment. A collision on an asteroid hundreds of millions of miles away, an impact so violent it reshaped an entire world, and pieces of that event ended up in our hands. It is one of the most direct physical connections we have between our planet and the asteroid belt. Every head meteorite is a messenger, carrying a story of destruction and transformation across the vast emptiness of space. Vesta is also interesting because it is one of the few asteroids that is differentiated, meaning its interior has separated into distinct layers, just like Earth. Vesta has an iron core, a rocky mantle, and a basaltic crust. This internal structure tells us that Vesta was once hot enough to be molten, which allowed the heavier elements to sink to the center and the lighter elements to float to the top. This process, called differentiation, is the same one that gave Earth its layered structure. It is a sign that Vesta was once a much more dynamic place, a world with its own internal heat engine, its own geological processes, its own story of transformation. The fact that Vesta differentiated while most other asteroids did not tells us something about the conditions in the early solar system. Vesta was large enough and formed early enough that it still retained heat from the radioactive decay of short-lived isotopes like aluminum-26. This internal heat melted Vesta's interior and allowed differentiation to occur. Smaller asteroids, which formed later or were just too small to retain heat, never went through this process. They remained cold and undifferentiated, their interiors a homogeneous mixture of rock and metal. So when we look at the asteroid belt, we are seeing a spectrum of development. On one end, you have primitive, undifferentiated asteroids that have barely changed since they formed 4.5 billion years ago. On the other end, you have differentiated bodies like Vesta that went through a period of internal activity before cooling down and becoming the cold, dead worlds they are today. And in between, you have every stage of development in between. The asteroid belt is like a museum of planetary formation, with exhibits representing every step of the process from raw material to fully formed world. Except the final exhibit, the completed planet, is missing, stolen by Jupiter before it could ever be finished. Let me take you even deeper now, because there is another aspect of the asteroid belt that most people never hear about, and it might be the most mind-bending of all. It has to do with the belt's relationship with water and the origins of life on Earth. You see, the early Earth was a hellish place. For hundreds of millions of years after it formed, our planet was bombarded by asteroids, comets, and other debris left over from the solar system's formation. This period is called the Late Heavy Bombardment, and it was a time of almost unimaginable violence. Massive impacts one after another, turning the surface into a sea of molten rock, boiling away any water that tried to accumulate, sterilizing the landscape over and over again. But eventually, the bombardment slowed. The rain of cosmic debris eased. And when it did, something remarkable happened. Water appeared on Earth's surface, vast quantities of it, enough to fill the oceans. But where did all that water come from? For a long time, scientists believed that Earth formed with its water already locked inside its rocks, and that this water was gradually released through volcanic activity. And while that is certainly part of the story, research over the past few decades has revealed that a significant portion of Earth's water was actually delivered from space. And one of the primary delivery vehicles was asteroids from the outer part of the asteroid belt. Remember those C-type asteroids I mentioned earlier? The dark, carbon-rich ones that make up about 75% of the belt? Many of these asteroids contain significant amounts of water, locked up inside minerals called hydrated silicates. These are minerals that have water, molecules chemically bonded within their crystal structures. The water is not liquid. It is not ice. It is trapped inside the rock itself at a molecular level. During the early history of the solar system, gravitational interactions with Jupiter and the other giant planets sent many of these water-bearing asteroids careening into the inner solar system. Some of them hit Earth, and when they did, the energy of the impact released the water locked inside their minerals. Over millions of years, delivery after delivery, these watery asteroids contributed a significant portion of the water that now fills our oceans. This means that every time you drink a glass of water, take a shower, swim in the ocean, or just look at a river flowing by, some of those water molecules may have been delivered to Earth by asteroids from the belt, the water in your body, the water in the clouds above your head, the water in every living thing on this planet. Some of it originated in the cold, dark region between Mars and Jupiter. The asteroid belt is not just a collection of dead rocks. It is the source of one of the most essential ingredients for life on Earth. And it is not just water. Those C-type asteroids also contain complex organic molecules, carbon-based compounds that are the building blocks of life, amino acids, the molecules that link together to form proteins, nucleobases, the molecules that make up DNA and RNA. These organic molecules have been found in meteorites that originated from C-type asteroids, and they are the same kinds of molecules that life on Earth is built from. So the asteroid belt may have contributed not only the water for life, but some of the actual chemical building blocks as well. The raw ingredients for biology delivered special express from the region between Mars and Jupiter. It is one of the most profound connections between the seemingly dead, empty asteroid belt and the vibrant, teeming world we live on. Our existence may owe a direct debt to those lonely rocks floating in the void. Now, I want to spend some time on something that I find incredibly fascinating, and it has to do with the way the asteroid belt was shaped by events that happened not in the belt itself, but far away, in the outer solar system. Because the story of the asteroid belt cannot be told without talking about something called the Nice model. Named after the city of Nice in France where it was first proposed. The Nice model is a theory about what happened in the outer solar system about 700 million years after the planets formed. According to this model, the giant planets Jupiter, Saturn, Uranus, and Neptune were not always in the positions they are in today. They started out in a much more compact arrangement, much closer together and much closer to the Sun than they are now. And then something happened that sent them migrating outward, The theory suggests that interactions between the giant planets and a massive disk of small icy bodies beyond their orbits caused the planets to gradually shift their positions. Saturn moved outward. So did Uranus and Neptune. In fact, Neptune may have moved outward dramatically, sweeping through a vast region of space and scattering icy bodies in every direction. This migration was not smooth and gradual. It may have involved sudden, violent gravitational interactions between the giant planets themselves, with Uranus and Neptune possibly swapping positions at one point. And during all of this chaos, Jupiter moved slightly inward, just a little bit closer to the Sun. But that small shift had enormous consequences for the asteroid belt. As Jupiter moved inward, it swept through new regions of the belt, destabilizing asteroids that had been in stable orbits for hundreds of millions of years. The migration sent waves of gravitational disruption rippling through the belt, scattering asteroids in every direction. Some were sent inward toward the terrestrial planets. Some were sent outward into deep space. Some were ejected from the solar system entirely. The belt lost a tremendous amount of mass during this period, perhaps the majority of whatever mass it still had at that point. This is thought to be the cause of the late heavy bombardment I mentioned earlier. The sudden destabilization of the asteroid belt and the scattering of icy bodies by Neptune's migration sent a storm of impacts raining down on the inner planets. The Moon's ancient, heavily cratered surface is a record of this bombardment. Many of the large impact basins on the Moon, including the one that formed the Sea of Rains and the Sea of Serenity, may have been created during this period. Earth would have experienced the same bombardment, but plate tectonics and erosion have erased most of the evidence from our planet's surface. So the asteroid belt, as we see it today, is not just the result of Jupiter preventing a planet from forming. It is also the result of a violent reshuffling of the entire outer solar system that occurred hundreds of millions of years later. The belt was depleted twice. Once during the initial formation period, when Jupiter's gravity prevented accretion, and again during the planetary migration event described by the Nice model. It is a wonder that any asteroids remain at all, but remain they have, and in their survival, they carry the memory of these ancient events. The distribution of asteroids in the belt, their orbits, their compositions, their sizes. All of these properties contain information about the violent history that shaped this region. Scientists can read the asteroid belt like a detective reads a crime scene, piecing together clues about events that happened billions of years ago. Let me shift gears now and talk about something that connects the asteroid belt to our everyday lives in a way that might surprise you. I am talking about meteorites, those rocks that fall from the sky and land on Earth's surface. Because many of the meteorites we find on Earth originated in the asteroid belt. When asteroids in the belt collide with each other, as they occasionally do even today, the impact can send fragments flying off into new orbits. If those new orbits happen to cross Earth's path, then over thousands or millions of years, those fragments can find their way to our planet. They enter our atmosphere at tremendous speeds, heating up and glowing as they streak across the sky. We call them meteors or shooting stars, and if any portion survives the fiery passage through the atmosphere and reaches the ground, we call it a meteorite. Meteorites come in many different varieties, reflecting the diversity of the asteroids they came from. Stony meteorites are the most common. They are made primarily of silicate minerals and look similar to ordinary rocks, which is why they often go unnoticed. Iron meteorites are much rarer but much more dramatic. They are dense chunks of nickel-iron alloy, clearly metallic and obviously not from Earth. When you hold an iron meteorite, You are holding a piece of an asteroid's core, a fragment of metal that crystallized billions of years ago deep inside a small world that has long since been destroyed. And then there are the most special meteorites of all, the ones called carbonaceous chondrites. These are fragments of those primitive C-type asteroids I mentioned earlier, and they are treasure troves of scientific information. Carbonaceous chondrites contain tiny structures called chondrules, which are small, round beads of rock that formed in the protoplanetary disk before the asteroids themselves. These chondrules are literally some of the oldest solid objects in the solar system. They predate the planets. They predate the asteroids. They are remnants from the very first moments of solid matter forming from the cloud of gas and dust that surrounded the young sun. Holding a carbonaceous chondrite is like holding a piece of the solar system's birth certificate. It is a direct physical connection to the moment when our cosmic neighborhood began to take shape. And the information locked inside these meteorites is extraordinary. Scientists have found amino acids in carbonaceous chondrites. Not just one or two types, but dozens of different amino acids, including some that are used by life on Earth and some that are not found in any living organism. This tells us that the chemistry of life is not unique to our planet. The building blocks of biology are produced naturally in space, in the cold, dark environments of the outer solar system and the asteroid belt. In 2020, scientists studying the Murchison meteorite, a famous carbonaceous chondrite that fell in Australia in 1969, announced that they had found a grain of silicon carbide inside it that was approximately 7 billion years old. That is older than the Sun, older than the solar system. This tiny grain was formed in the atmosphere of a dying star that existed before our Sun was born. It floated through interstellar space, was incorporated into the cloud of material that eventually formed our solar system, and ended up embedded in an asteroid that eventually fell to Earth. A single grain, carrying a story that spans the life and death of stars. These presolar grains, as they are called, are among the most remarkable objects ever found. They are physical samples of other stars, tiny pieces of alien solar systems that predate our own. And they are found in meteorites that come from the asteroid belt. The belt is not just a record of our own solar system's history. It contains fragments from before our solar system even existed. It is a library that holds chapters from multiple cosmic stories, all preserved in the cold, dark space between Mars and Jupiter. Let me take you on another detour now, because I want to explore something that gets to the heart of what makes space so profoundly moving. It is the silence, the absolute, total, overwhelming silence of the asteroid belt and of space in general. On Earth, we are surrounded by sound. It is so constant and so pervasive that we barely notice it. The hum of traffic, the rustling of leaves, the distant barking of a dog, the murmur of conversation. Even in the quietest places on Earth, there is still the sound of your own heartbeat, the rush of blood in your ears, the subtle creaking of your body as it moves. We are never truly in silence, but in the asteroid belt, there is nothing. Sound requires a medium to travel through. It needs air or water or rock, something that can vibrate and carry the wave from one place to another. In space, there is no medium. There is just vacuum, emptiness. And in emptiness, sound cannot exist. So the asteroids float through their orbits, in perfect, absolute silence. When two asteroids collide, as they occasionally do, the impact produces no sound at all. The rocks shatter and fragment and send debris flying in every direction, and all of it happens in total silence. If you were standing on a nearby asteroid watching the collision, you would see the flash of the impact. see the debris expanding outward in a cloud of tumbling fragments, but you would hear absolutely nothing. It would be like watching a movie with the sound turned completely off. There is something deeply unsettling about that. We are wired to associate catastrophic events with noise. Explosions should roar, collisions should crash, destruction should be loud. But in space, the most violent events occur in complete and utter stillness. Stars explode, planets collide, asteroids shatter, and none of it makes a sound. The universe conducts its most dramatic business in absolute silence, like a stage play performed by mute actors in an empty theatre. And it is not just the silence, it is the darkness too. The asteroid belt, despite being closer to the Sun than many other regions of space, is still an incredibly dark place. The Sun, from the distance of the belt, appears much smaller than it does from Earth. It is still the brightest object in the sky by far, but it is noticeably less intense. And away from the Sun, the darkness is profound. There are no city lights, no atmospheric glow, no reflected light from clouds or oceans. Just the pure, unfiltered blackness of space, punctuated by the sharp, unwavering points of distant stars. An asteroid floating through this darkness is a lonely thing. It has been orbiting the Sun for billions of years, following the same path, spinning slowly on its axis, its surface alternating between the dim warmth of sunlight and the bitter cold of shadow. No one has ever visited it. No one has ever seen it up close. No one even knows it exists, unless it happens to be large enough to be detected by telescopes on a planet hundreds of millions of miles away. Most asteroids in the belt have never been observed at all. They are anonymous, unknown, unnamed. Billions of years of quiet existence, unwitnessed and unrecorded. There is a strange beauty in that anonymity. These objects do not need to be observed to exist. They do not need to be named to matter. They simply are. They orbit, they spin. They occasionally bump into each other, and they carry on. They have been doing this since before life existed on Earth, since before the Earth itself was fully formed. And they will continue doing it long after humanity is gone, long after the Earth has been swallowed by the expanding Sun, long after the Sun itself has burned out and faded to a cold, dark ember. The asteroid belt does not care about us. It was here before us, and it will be here after us. And there is something both humbling and oddly comforting about that. In a world where everything seems urgent and important and demanding of our attention, the asteroid belt just sits there, quiet and patient, doing what it has always done, orbiting, spinning, waiting, not waiting for anything in particular, just existing, in the most basic, fundamental sense of the word. Now, let us come back to something more concrete. I want to talk about the structure of the belt in more detail, because it is not the uniform ring of debris that most diagrams suggest. The asteroid belt actually has distinct regions, each with its own character and its own population of asteroids. The inner belt, closest to Mars, is dominated by S-type asteroids. These are the rocky, silicate-rich asteroids that formed in the warmer regions of the protoplanetary disk. They tend to be brighter and more reflective than the darker C-type asteroids that dominate the outer belt. The transition from S-type to C-type as you move outward through the belt corresponds to what scientists call the snow line, the distance from the Sun beyond which it was cold enough for water and other volatiles to condense into ice during the solar system's formation. Inside the snow line, only rock and metal could survive in solid form. Water and other ices were vaporized by the Sun's heat. This is why the inner asteroids are made primarily of rock and metal. But beyond the snow line, in the outer part of the belt, temperatures were low enough for ice to remain solid. This is why the outer asteroids, the C-types, contain water and other volatiles locked inside their minerals. The composition of the asteroids changes with distance from the Sun, and this gradient tells us about the temperature profile of the protoplanetary disk 4.5 billion years ago. But this neat, orderly gradient has been somewhat mixed up over the eons. Jupiter's gravitational stirring and the planetary migration events I described earlier have shuffled some asteroids around, moving some inner belt objects outward and some outer belt objects inward. The belt is not as neatly organized today as it was when it first formed. But the general trend still holds. Rocky asteroids dominate the inner belt, and carbon-rich, water-bearing asteroids dominate the outer belt. Within the belt, asteroids are not distributed evenly. They tend to cluster in groups and families. Asteroid families are collections of asteroids that share similar orbits and compositions, and they are thought to be the fragments of a single larger body that was broken apart by a catastrophic collision. When a large asteroid is hit by another asteroid at high speed, it can be completely shattered, producing hundreds or thousands of smaller fragments that continue to orbit the Sun in roughly the same path as the original object. Over time, these fragments slowly spread out, but they retain enough similarity in their orbits and compositions that scientists can identify them as members of the same family. Some of the largest asteroid families contain thousands of known members. The Flora family, in the inner belt, is one of the largest and is thought to be the remnant of a catastrophic collision that occurred about 1 billion years ago. The Eos family, in the outer belt, contains over 4,000 known members. And there are dozens of other families scattered throughout the belt, each one a record of an ancient destruction event. These families are like forensic evidence of the belt's violent past. By studying the orbits and compositions of family members, scientists can work backward to determine the size of the original body, the velocity of the impactor, and even the approximate time of the collision. Each family tells the story of a specific moment of destruction, frozen in the orbital dynamics of the surviving fragments. And some of these destruction events were truly spectacular. The collision that created the Rhea Silvia Basin on Vesta, which I mentioned earlier, was one of the most powerful impacts to occur in the belt in relatively recent geological history. The impactor that hit Vesta was estimated to be about 30 miles across, and it struck with enough force to blast a crater nearly as wide as Vesta itself. The debris from this impact formed the Vesta family of asteroids, and some fragments, as I mentioned, eventually made it all the way to Earth as head meteorites. But even the Rhea Silvia impact pales in comparison to the collisions that occurred during the earliest days of the solar system. In those chaotic first 100 million years or so, when the planetesimals were still trying to assemble themselves into planets, collisions were far more frequent and far more energetic. Bodies tens or even hundreds of miles across were smashing into each other at speeds of miles per second. These titanic impacts are what shaped the asteroid belt into its present form, grinding down the original planetesimals into the smaller fragments we see today. It is hard to overstate the violence of those early days. Imagine a region of space filled with rocky bodies, some as large as small states, all moving on crossing orbits, all subject to Jupiter's gravitational stirring, all crashing into each other with devastating regularity. The energy released by these collisions was immense, enough to melt rock, vaporize metals, and reshape entire worlds in an instant. And all of it happened in perfect silence, in the cold darkness between Mars and Jupiter, witnessed by nothing and no one. The asteroid belt we see today is the quiet aftermath of that ancient war. The scattered remains of a battlefield where worlds were broken and futures were stolen. And in the silence and darkness of that aftermath, the surviving fragments continue their endless orbits, carrying the scars of those ancient battles on their surfaces and in their compositions. I find myself drawn to the poetic nature of this story, because the asteroid belt is, in many ways, a memorial, a monument to potential that was never realized, a reminder that not everything in the universe gets to fulfill its potential. Sometimes the conditions are not right. Sometimes the forces at work are too powerful to overcome. Sometimes a planet just does not get to be born. And yet, even in its failure to become a planet, the asteroid belt has played an incredibly important role in the history of our solar system. It delivered water and organic molecules to Earth. It shaped the orbital dynamics of the inner planets through ancient bombardments. It continues to serve as a source of meteorites that teach us about the earliest days of our cosmic neighborhood. And it serves as a natural laboratory where scientists can study the building blocks of planets without the complications introduced by geological activity, atmospheres, and other planetary processes. The asteroid belt is not a failure. It is something different, something unexpected, something that turned out to be valuable in ways that a fifth planet between Mars and Jupiter never could have been. If that planet had formed, we might not have received the water and organic molecules that the belt delivered to Earth. We might not have the meteorites that have taught us so much about our origins. We might not even be here at all. And that brings us to what I think is the most profound aspect of the asteroid belt story: the connection between Jupiter's gravitational bullying, the belt's failed planet, and the existence of life on Earth. Jupiter is often called Earth's protector. You have probably heard this idea before. The thinking goes that Jupiter's massive gravity acts as a cosmic shield, deflecting asteroids and comets away from the inner solar system and preventing them from hitting Earth. And there is some truth to this. Jupiter does capture some objects that might otherwise pose a threat. The famous impact of Comet Shoemaker-Levy 9 into Jupiter in 1994 was a dramatic demonstration of Jupiter's ability to absorb cosmic debris. But the full story is more complicated than that. Jupiter does not just deflect objects away from Earth. It also sends objects toward Earth. Its gravitational influence can redirect asteroids from the belt onto orbits that cross Earth's path. So Jupiter is both a shield and a source of danger, depending on the specific circumstances. The same gravitational force that can deflect one asteroid away from us can redirect another one straight at us. However, the overall balance seems to be in our favor. Studies have suggested that without Jupiter, the rate of large impacts on Earth would be significantly higher, not because Jupiter deflects everything, but because without Jupiter, the asteroid belt would be much more massive. Remember, Jupiter depleted the belt of most of its original mass. If Jupiter were not there, or if it were much smaller, the belt would contain far more material, and that material would be more loosely bound, making it easier for objects to escape the belt and head toward the inner planets. So, in a roundabout way, Jupiter's gravitational bullying of the asteroid belt may have been essential for life on Earth. By preventing a planet from forming, and by stripping the belt of most of its mass, Jupiter reduced the amount of dangerous debris in the inner solar system. Fewer large asteroids near Earth means fewer catastrophic impacts, which means more time for life to evolve and develop without being interrupted by extinction-level events. It is a delicious irony. The same force that destroyed one world's potential may have been necessary for another world to thrive. The asteroid belt's loss was, in a very real sense, Earth's gain. The planet that never got to be born made it possible for life to flourish on the planet that did. Now, I want to take you even further back in time to explore what I think is one of the most dramatic chapters in the asteroid belt story. And this involves something called the Grand Tack. The Grand Tack hypothesis is a theory about what Jupiter did in the very earliest days of the solar system, when the planets were still forming from the protoplanetary disk. According to this model, Jupiter did not just sit in one place while the solar system took shape around it. It moved, and it moved a lot. The theory goes like this. Jupiter was the first giant planet to form, emerging from the protoplanetary disk relatively quickly. As it grew, it began to interact with the gas in the disk around it. This interaction caused Jupiter to migrate inward toward the Sun, not slowly, relatively quickly on astronomical timescales. Jupiter may have migrated all the way inward to roughly where Mars orbits today, about 1.5 times Earth's distance from the Sun. Now, think about what that means. Jupiter, the most massive planet in the solar system, barreling inward through the region where the terrestrial planets were trying to form. Its gravity would have been like a wrecking ball, scattering the building materials of the inner solar system, disrupting the formation of rocky worlds, and fundamentally reshaping the distribution of material in the disk. This inward migration would have been catastrophic for the material in the inner solar system if it had continued. But it did not continue because Saturn came to the rescue. Saturn, the second giant planet to form, also began migrating inward through the disk. When Saturn caught up to Jupiter and the two planets fell into a specific orbital resonance with each other, their combined gravitational interaction with the disk reversed direction. Instead of continuing inward, Jupiter began to migrate outward again, back toward the outer solar system. This reversal is the tack in Grand Tack, named after a sailing maneuver where a boat changes direction by turning into the wind. Jupiter migrated outward until it reached roughly its current position, about 5 times Earth's distance from the Sun. And as it did so, it swept through the asteroid belt region twice. Once on the way in, and once on the way out. Each passage was devastatingly destructive, scattering asteroids and depleting the region of most of its mass. But the outward passage also did something constructive. As Jupiter moved outward through the disk, it scattered material from the outer, colder regions of the disk inward into the asteroid belt. This is thought to be the origin of the C-type asteroids in the outer belt. They did not form in the belt. They were deposited there by Jupiter's outward migration, transplanted from colder regions further from the Sun. This is why the asteroid belt contains such a diverse mix of asteroid types. The rocky S-type asteroids in the inner belt formed more or less where they are now, in the warmer regions close to the Sun. But the water-rich C-type asteroids in the outer belt were brought there from further out, carried inward by Jupiter's gravitational wake as it migrated back toward its current position. The belt is not just a single population of locally formed objects. It is a mixture of materials from different parts of the solar system, assembled by the migrations of the giant planets. The Grand Tack also helps explain why Mars is so small. If Jupiter migrated inward to roughly Mars's current orbit, it would have swept up or scattered much of the material that Mars needed to grow. This left Mars with a limited supply of building material, which is why Mars is only about 1/10 the mass of Earth. Without Jupiter's inward migration, Mars might have been much larger, perhaps even Earth-sized. So Jupiter did not just affect the asteroid belt, it shaped the entire architecture of the inner solar system, determining the sizes and positions of the terrestrial planets. This is one of those ideas that makes your head spin when you really think about it. The planet we live on, the size it is, the distance it is from the sun, the amount of water it has, all of these things may have been determined, at least in part, by the migration of a gas giant billions of years ago. The conditions that make Earth habitable are not just a result of our planet's own properties. They are the product of a complex dance between all the planets in the solar system, a dance that began 4.5 billion years ago and that shaped everything we see today. And the asteroid belt sits right at the center of this story. It is both a victim and a product of the giant planet's migrations. It was depleted and scattered and disrupted by Jupiter's movements, but it was also enriched and diversified by the same process. The belt we see today is a palimpsest, a document that has been written over multiple times, each layer of writing telling a different story from a different era. Let me now turn to something that has captured a lot of public attention in recent years, and that is the idea of mining the asteroid belt. Asteroid mining, the concept of sending spacecraft to asteroids to extract valuable resources and bring them back to Earth or use them in space. It sounds like science fiction, and in many ways it still is. But it is science fiction that is slowly becoming science fact. The asteroids in the belt contain enormous quantities of valuable materials. Metals like iron, nickel, cobalt, and platinum group metals. Water, which could be split into hydrogen and oxygen for rocket fuel. Rare earth elements that are essential for modern technology. Some individual asteroids are estimated to contain more platinum than has ever been mined in all of human history. The economic potential is staggering, but the practical challenges are equally staggering. The asteroid belt is far away. Even at its closest point, the inner edge of the belt is over 100 million miles from Earth. Getting there requires a long journey, typically several years with current propulsion technology. And once you arrive, you need to navigate to a specific asteroid, match its orbit and rotation, land on its surface, extract resources, and then transport those resources back to Earth or to wherever they are needed. The energy requirements for such a mission are enormous. The engineering challenges are immense, and the economics, at least for now, do not quite work out. Meteorites. It costs so much to launch spacecraft and travel to the belt that the value of the resources you bring back would need to be extraordinarily high to justify the expense. But that calculation is slowly changing. As launch costs continue to drop, thanks to reusable rockets and other innovations, the break-even point for asteroid mining is moving closer. And the value of certain resources, particularly rare earth elements and platinum group metals, continues to rise as demand grows. Some forward-thinking companies and investors are already positioning themselves for a future in which asteroid mining is not just possible, but profitable. The first asteroid mining operations will probably not take place in the main belt, however. They will likely target near-Earth asteroids, which are objects that have been knocked out of the belt and into orbits that bring them close to our planet. These are much easier to reach than the main belt, requiring less fuel and shorter travel times. Some near-Earth asteroids pass closer to us than the Moon, making them accessible with relatively modest spacecraft. But in the longer term, the main belt represents the mother lode. The sheer quantity of resources out there is almost beyond comprehension. If humanity ever becomes a truly spacefaring civilization, with colonies on Mars and the Moon, and space stations scattered across the inner solar system, The asteroid belt will be the quarry from which we build our future. The failed planet will become the raw material for a new chapter in human history. There is something poetically fitting about that. The asteroid belt, the region where a planet was never allowed to form, becoming the source material for human expansion into space. The building blocks that were never assembled into a world being harvested and used by a species that evolved on a different world. It is as if the belt has been waiting 4.5 billion years for someone to come along and finally put those scattered bricks to use. But for now, the belt remains quiet, untouched, unchanged. Its asteroids continue their endless orbits, just as they have since the dawn of the solar system. And there is no rush. They will still be there when we are ready. Let me shift direction once more and talk about something that connects the asteroids belt to the broader question of whether we are alone in the universe. Because the belt has taught us something important about the conditions necessary for life. And that lesson has implications for how we think about life on other worlds. We now know that the asteroid belt, specifically the C-type asteroids in the outer belt, played a role in delivering water and organic molecules to Earth. This means that the presence of a belt-like region in a solar system might be an important factor in determining whether a planet can develop and sustain life. If a rocky planet needs water delivered from an external source, and if that source is an asteroid belt enriched with water-bearing asteroids, then the arrangement of a solar system, including the presence and position of giant planets and asteroid belts, could be a key ingredient in the recipe for a habitable world. This raises fascinating questions about other solar systems. We now know that planets are incredibly common in our galaxy. Almost every star has at least one planet, and many have multiple planets. Some of these systems have giant planets similar to Jupiter. Some have rocky planets in the habitable zone, the region around a star where liquid water could exist on a planet's surface. But do they have asteroid belts? And if they do, are those belts enriched with water and organics the way ours is? We do not have definitive answers to these questions yet, but we are making progress. Astronomers have detected debris disks around many other stars, disks that may be analogous to our asteroid belt. Some of these disks show signs of being shaped by the gravitational influence of giant planets, just as our belt has been shaped by Jupiter. The presence of these disks suggests that asteroid belts may be a common feature of planetary systems, which in turn suggests that the delivery of water and organics to rocky planets via asteroids might be a common process in the universe. If that is the case, then the conditions for life might be more common than we previously thought. The asteroid belt, far from being a quirky, unimportant feature of our solar system, might be a key piece of the puzzle that makes life possible. And similar belts around other stars might be doing the same thing for other planets right now, delivering the ingredients for life to worlds that we have not even discovered yet. It is a mind-expanding thought. Every time we learn something new about our asteroid belt, we are potentially learning something about the billions of other asteroid belts that may exist throughout the galaxy. Our belt is a template, a case study, a worked example that we can use to understand processes that might be unfolding around countless other stars. Now, I want to bring you back to the belt itself one more time, because there is one more story I want to tell, and it is a story about Trojan asteroids. You might have heard of the Trojan asteroids of Jupiter. These are asteroids that share Jupiter's orbit around the Sun, but they do not orbit near Jupiter itself. Instead, they cluster at two special points along Jupiter's orbital path. One group about 60 degrees ahead of Jupiter, and the other about 60 degrees behind. These points are called Lagrange points, specifically L4 and L5, and they are gravitational sweet spots where the combined gravitational pull of the Sun and Jupiter creates a stable region where objects can remain for billions of years. The Trojan asteroids are not technically part of the main asteroid belt. They orbit at Jupiter's distance from the Sun, which is beyond the outer edge of the belt, but they are closely related to the belt's story because many of them are thought to have originated in the same region of the protoplanetary disk and were captured into their current positions during the planetary migration events described by the Nice model. There are a lot of Trojan asteroids. Scientists estimate that there may be as many Trojans as there are asteroids in the main belt itself. The leading group at L4 is called the Greek camp, while the trailing group at L5 is called the Trojan camp. These names come from characters in Homer's Iliad, and individual asteroids in each group are named after heroes from the respective sides of the Trojan War. NASA is currently conducting a mission to study the Trojan asteroids up close. The Lucy spacecraft, launched in 2021, is on a 12-year journey that will take it past multiple Trojan asteroids. By the time its mission is complete, Lucy will have visited more individual asteroids than any previous mission in history. The data it collects will help scientists understand the origin and evolution of these mysterious objects and their relationship to the main belt. The Trojans are fascinating because they may represent a population of asteroids that has been trapped in the same orbits for billions of years, essentially frozen in place since the early days of the solar system. If that is the case, they could provide an even more pristine record of early solar system conditions than the main belt asteroids, which have been more heavily processed by collisions and gravitational interactions over the eons. And speaking of missions to the asteroid belt, let me touch on a few more that deserve mention. In addition to Dawn, OSIRIS-REx, Hayabusa, Hayabusa 2, Psyche, and Lucy, there have been and continue to be numerous other missions that have contributed to our understanding of asteroids. The Near Shoemaker mission, launched in 1996, was the first spacecraft to orbit an asteroid. Its target was 433 Eros, a near-Earth asteroid about 21 miles long. Near Shoemaker spent a year orbiting Eros, mapping its surface in extraordinary detail before performing a controlled landing on the asteroid's surface in 2001. This was a remarkable achievement, as the spacecraft was not designed for landing. It touched down gently and continued to transmit data from the surface for over 2 weeks before contact was lost. The European Space Agency's Rosetta mission, while primarily focused on studying a comet, also flew past 2 asteroids on its way to its target. It visited the asteroid Steins in 2008 and the asteroid Lutetia in 2010, providing valuable close-up observations of both objects. And in 2022, NASA conducted one of the most ambitious asteroid missions ever attempted. The DART mission, which stands for Double Asteroid Redirection Test, was designed to test whether humanity could intentionally change the orbit of an asteroid by crashing a spacecraft into it. The target was Dimorphos, a small moon orbiting a larger asteroid called Didymos. The DART spacecraft successfully impacted Dimorphos at a speed of roughly 4 miles per second, and subsequent observations confirmed that the impact had measurably changed Dimorphos's orbit around Didymos. This was a landmark moment in human history. For the first time, we demonstrated the ability to alter the trajectory of a celestial body. If a dangerous asteroid were ever discovered on a collision course with Earth, the DART technique, or something similar, could potentially be used to deflect it. We went from being a species entirely at the mercy of asteroid impacts to one that has at least a basic capability to defend itself. And that capability was developed, in part, because of what we have learned from studying the asteroid belt. The belt has taught us about the diversity of asteroid compositions and structures. It has shown us that some asteroids are solid rock, while others are loose rubble piles. This knowledge is crucial for planetary defense, because the strategy you would use to deflect a solid asteroid is very different from the strategy you would use for a rubble pile. Without the decades of research on belt asteroids, we would be far less prepared to deal with the threat of an impact. Let me take one more deep dive before we begin to bring this journey to a close. I want to talk about what the future holds for the asteroid belt, not in terms of human activity, but in terms of the belt's own natural evolution. Because the belt is not static, it is slowly, imperceptibly changing even now. Over the next few billion years, the asteroid belt will continue to lose mass. Collisions between asteroids will continue to produce smaller and smaller fragments. Some of those fragments will be ejected from the belt by Jupiter's gravity. Others will spiral inward toward the Sun, due to a subtle effect called the Yarkovsky effect. The Yarkovsky effect is a gentle but persistent force that acts on small asteroids due to the way they absorb and re-emit sunlight. When an asteroid is warmed by the Sun, it absorbs energy on its sunlit side. As the asteroid rotates, that warm side turns away from the Sun and radiates the absorbed energy back into space as heat. This radiation creates a tiny, tiny push, so small that it is virtually undetectable on human timescales. But over millions of years, that tiny push accumulates, gradually changing the asteroid's orbit. Depending on the asteroid's rotation direction, the Yarkovsky effect can either push it closer to the Sun or further away. For small asteroids, this effect can be significant over long periods. It slowly migrates them out of the main belt and into orbits that cross the paths of the inner planets. This is one of the main mechanisms by which asteroids leave the belt and become near-Earth asteroids. The Yarkovsky effect is a slow, patient force that quietly reshapes the distribution of asteroids over millions and billions of years. Another process that contributes to the belt's evolution is called the Yorp effect, which is related to the Yarkovsky effect, but acts on the asteroid's rotation rather than its orbit. The Yorp effect can speed up or slow down an asteroid's spin, and in extreme cases, it can spin an asteroid so fast that it breaks apart. This is thought to be one of the mechanisms that creates rubble pile asteroids and binary asteroid systems. The Yorp effect spins a solid asteroid faster and faster until centrifugal force overcomes the strength of the rock, and the asteroid literally flies apart. The resulting fragments then reassemble under their own gravity into a loose rubble pile, or in some cases, two separate objects orbiting each other. These processes, the Yarkovsky effect, the Yorp effect, collisions, and gravitational interactions with Jupiter, are all working together to slowly erode the asteroid belt. The belt is losing mass, losing asteroids, and slowly fading over time. In a few billion years, it will be even more depleted than it is today. Eventually, in the very distant future, the asteroid belt as we know it may cease to exist entirely. Its asteroids either absorbed by planets, ejected from the solar system, or ground down to dust. But we do not need to worry about that. The timescales involved are so vast that the belt will outlast humanity by a comfortable margin. For all practical purposes, the asteroid belt is eternal. Or at least, it will persist for as long as the Sun continues to shine, which is another 5 billion years or so. And when the Sun does die, something interesting will happen to the asteroid belt. As the Sun expands into a red giant star in about 5 billion years, its outer layers will engulf the inner planets. Mercury, Venus, and possibly Earth will be consumed. Mars might survive, but it will be scorched and transformed. And the asteroid belt, sitting beyond Mars, will be heated like never before. The ice is locked. Inside, the C-type asteroids will evaporate. The surfaces of asteroids will be altered by the intense radiation. The belt will be transformed, but it will likely survive, at least in some form. After the Sun sheds its outer layers and collapses into a white dwarf, the asteroid belt will be bathed in the dim, fading light of a dying star. The asteroids will continue to orbit, now around a stellar corpse, their surfaces gradually cooling in the diminishing glow. They will orbit in silence, in darkness, in cold, just as they have always done. Except now, there will be no Earth to look up from, no telescopes to study them, no minds to wonder about their origins. They will simply be lonely rocks orbiting a dead star in a universe that has moved on. There is something hauntingly beautiful about that image. The asteroid belt, outlasting the planets, outlasting the Sun, outlasting life itself. The most ancient and most patient inhabitants of our solar system, continuing their quiet existence long after everything else has ended. It is a reminder that the universe does not operate on human timescales. It does not share our sense of urgency or our need for meaning. It simply is on its own terms, for its own incomprehensible reasons. But let us come back to the present, because the asteroid belt is not just a relic of the past or a vision of the far future. It is a living, dynamic region of space that is relevant to us right now. Every year, dozens of meteorites that originated in the asteroid belt fall to Earth's surface. Most of them go unnoticed, landing in oceans, forests, deserts, and other uninhabited areas. But some are found, and each one is a gift from the belt, a physical sample delivered free of charge from a region of space that would cost billions of dollars to visit. Scientists collect these meteorites, study them in their laboratories, and extract from them the secrets of the solar system's past. The analysis of meteorites has led to some of the most important discoveries in planetary science. It was the study of meteorites that first revealed the age of the solar system, about 4.5 billion years. It was meteorites that taught us about the composition of the protoplanetary disk. It was meteorites that showed us that water and organic molecules are common in the outer solar system. And it was meteorites that gave us our first direct evidence of pre-solar grains, tiny pieces of other stars embedded in the fabric of our own solar system. Every time a meteorite lands on Earth, the asteroid belt is literally reaching out to us, tapping us on the shoulder, saying, "Hey, pay attention. I have something to tell you." And every time we pick up that meteorite and study it, we learn something new about ourselves and our place in the cosmos. I also want to take a moment to talk about the cultural impact of the asteroid belt, because while scientists study the belt through telescopes and spacecraft, the rest of us interact with it through stories, movies, books, and games. The asteroid belt has been a staple of science fiction for over a century, and its portrayal in popular culture has shaped how most people think about this region of space. In most science fiction, the asteroid belt is depicted as a dense, dangerous field of tumbling rocks. From the asteroid chase scene in a certain space opera to the mining colonies of countless video games, the belt is portrayed as a place of peril and adventure. A frontier zone where brave pilots navigate through deadly obstacles and where fortunes can be made or lost in the search for valuable minerals. This portrayal is wrong in almost every respect, as we have discussed. but it has given the asteroid belt a mythic quality in our collective imagination. It has made the belt into a symbol of danger, adventure, and the unknown. And while the reality is far quieter and far emptier than the fiction, the sense of wonder that the belt inspires is very real, because the asteroid belt is a frontier, not in the dangerous, action-packed sense of the movies, but in a deeper, more philosophical sense. It is a region of space that we are only just beginning to understand. Every mission we send there reveals something unexpected. Every meteorite we study overturns some assumption or opens a new line of inquiry. The belt is full of surprises, and it has been surprising us for over 2 centuries, ever since Giuseppe Piazzi spotted Ceres on that New Year's Day in 1801. And the surprises are not slowing down. Recent discoveries have shown that some asteroids may have active geological processes. Others may have subsurface oceans. Some contain minerals that do not exist naturally on Earth. The belt is a cornucopia of scientific wonders, and we have barely scratched the surface of what it has to teach us. Now, as we begin to wind down this journey, I want to talk about something that I think ties everything together, and that is the concept of the asteroid belt as a cosmic time capsule. Everything in the asteroid belt is old, staggeringly, incomprehensibly old. The asteroids themselves formed 4.5 billion years ago, in the first few million years of the solar system's existence. The materials they are made of are even older. Some of the pre-solar grains found in meteorites from the belt are 7 billion years old, predating our solar system by billions of years. When we study the asteroid belt, we are looking backward in time, not through light that has traveled from distant stars, but through physical objects that have preserved the conditions of their formation like flies trapped in amber. The asteroids have not changed significantly since they were made. They have not been resurfaced by volcanoes or worn down by wind and rain. They are, in many cases, exactly as they were when the solar system was brand new. This makes the asteroid belt one of the most valuable scientific resources in the solar system. It is a fossil record, a geological archive, a library of stones that contains information about the birth of our world and everything in it. And unlike most fossils, these ones are still out there, orbiting the sun, accessible to anyone with the technology and the will to go study them. The missions that are currently underway, Psyche, Lucy, and others, will add enormously to our understanding of this archive. But they are just the beginning. In the coming decades, as our technology improves and our ambitions grow, we will send more missions to the belt. We will visit more asteroids, collect more samples, make more discoveries. And each discovery will bring us closer to understanding the full story of how our solar system was born, how it evolved, and how it gave rise to the conditions that made life possible on at least one small blue world. That story is written in the asteroid belt, in the compositions of its rocks, in the orbits of its fragments, in the Kirkwood gaps carved by Jupiter's gravity, in the bright salt deposits on Ceres, in the metallic gleam of Psyche, in the rubble pile structure of Bennu, in the ancient chondrules preserved inside carbonaceous chondrites. Every piece of the belt is a page in that story, and we are only just learning to read it. So the next time someone mentions the asteroid belt, I hope you will think of it differently than you used to. Not as a dangerous minefield or a boring collection of rocks, but as what it truly is: a graveyard of an unborn world, a delivery service that brought the ingredients for life to Earth, a museum of the solar system's earliest days. A cosmic time capsule that has been waiting 4.5 billion years for someone to come along and open it, And in the grand sweep of cosmic history, we are the ones who get to open it. We are the first species on this planet, perhaps the first species anywhere, to develop the technology and the curiosity to reach out across hundreds of millions of miles of space and touch these ancient relics, to pick them up, examine them, and begin to understand the story they tell. That is a privilege that I do not think we fully appreciate. Out of all the species that have ever lived on Earth, out of all the billions of years of life's history on this planet, we are the first to send spacecraft to the asteroid belt. We are the first to hold meteorites and understand what they are. We are the first to glimpse the story of our own origins, written in the compositions of rocks that formed before our planet existed. And the story is not finished. There is so much more to learn, so many more asteroids to visit, so many more secrets to uncover. The asteroid belt is patient. It has been waiting since before the Earth existed, and it will wait for as long as it takes. But let us not keep it waiting too long. I want to take us through one more journey before we close our eyes tonight. Imagine you are floating in the asteroid belt right now, not in a spacecraft, just floating, suspended in the void between Mars and Jupiter, surrounded by nothing but space. The sun is visible, but distant. It is a bright point of light, brighter than any star, but noticeably smaller than it appears from Earth. It casts a faint warmth on your skin, but it is not the comforting embrace you know from a sunny day on Earth. It is thin, pale, distant. You can feel it, but only barely. Around you, there is nothing. Absolutely nothing. No rocks tumbling past, no asteroid in sight. Just darkness in every direction, stretching out to infinity. The stars are extraordinary, though. Without an atmosphere to blur and scatter their light, they are sharp and steady, pinpricks of perfect light scattered across the velvet blackness. The Milky Way stretches overhead like a river of light, more vivid and detailed than you have ever seen it from Earth. You can see Jupiter. It is bright, much brighter than it appears from Earth, because you are so much closer to it. It shines with a steady golden light, visibly larger than a point, but still not as large as the moon appears from Earth. It is just a brilliant dot, hanging in the darkness, quietly exerting its gravitational influence on everything around it, including you. And in this moment, floating in the silence and darkness, you realize something profound. You are part of this. You are made of the same stuff as those invisible asteroids floating in the emptiness around you. The iron in your blood was forged in the hearts of stars. The carbon in your muscles was assembled in the same protoplanetary disk that made the asteroids. The water in your cells may have been delivered to Earth by a C-type asteroid from this very region of space, billions of years ago. You are not separate from the asteroid belt. You are connected to it, in the most literal, physical, molecular sense. The atoms in your body have been on a journey that stretches back to the birth of the solar system and beyond. And some of those atoms spend billions of years floating in this very region of space, in this quiet darkness between Mars and Jupiter, before finding their way to Earth, into the oceans, into the web of life, and eventually into you. That connection is real. It is not metaphorical or poetic. It is physical, chemical, and provable. You carry the asteroid belt with you everywhere you go. It is in your bones and in your breath. And when you look up at the night sky and think about the vast, empty stretch of space between Mars and Jupiter, you are, in a very real sense, looking at your own origins. That is the secret of the asteroid belt. Not that it is dangerous or exciting or full of treasure, but that it is familiar. It is home, in the deepest sense of the word. the place where some of the ingredients for your existence were stored for billions of years before, being delivered, special delivery, to the young Earth. And now, as you float in that silence, let yourself feel the weight of that connection. 4.5 billion years of cosmic history, all leading to this moment. All those collisions, all those migrations, all those quiet orbits in the dark, all leading, eventually, improbably, miraculously, to you. The asteroid belt does not need us to give it meaning. It has existed for billions of years without being observed or understood, and it will continue to exist for billions more. But we have the ability to observe it, to understand it, and to see ourselves in it. And in doing so, we give meaning not to the belt, but to ourselves. We are the universe looking back at itself, trying to understand how it all began. And the asteroid belt, that quiet, dark, nearly empty stretch of space between Mars and Jupiter, is one of the best places to look. So as you drift off to sleep tonight, carry that thought with you. You are connected to the stars, to the asteroids, to the very fabric of the solar system. You are made of cosmic stuff, assembled from ingredients that have been on a journey of billions of years. And the asteroid belt, that misunderstood, underappreciated region of space, played a role in making you possible. Let that thought settle over you like a blanket. Let it warm you in the way that the distant sun warms the surfaces of those lonely asteroids. And as the darkness of sleep begins to close in, know that it is the same darkness that surrounds those ancient rocks, the same quiet, the same stillness, the same patient, enduring peace that has filled the space between Mars and Jupiter since before time had a name. You are not alone in that darkness. You never were. The asteroids have been there all along, floating through the void, carrying their stories, carrying their secrets, carrying, in some small way, the recipe for you. And they will be there tomorrow night, and the night after that, and every night for as long as the sun continues to shine. Sleep well, and dream of asteroid belts. And before you drift away completely, let me ask you something. Where in the world are you listening from right now? What time is it where you are? Drop it in the comments. I love seeing how our sleepy science community stretches across the entire globe. It always blows my mind to think that some of you are listening at midnight, while others are catching this during a lazy afternoon nap. Wherever you are and whatever time it is, thank you for spending it here, floating through the asteroid belt with me. If you enjoyed this journey, go ahead and tap that subscribe button so you do not miss the next trip. We have got so many more corners of the cosmos to explore together, and I promise each one is just as strange and beautiful as this one. Leave a comment and tell me what part of the asteroid belt surprised you the most. Was it the void paradox? The unborn planet? Ceres and its hidden ocean? I want to hear from you. And with that, I will let you go. Close your eyes. Let the silence of the belt wash over you. Let the darkness embrace you. And when you wake up tomorrow, remember that you carry the asteroid belt with you, in your bones, in your blood, in every glass of water you drink and every breath you take. Good night from the space between Mars and Jupiter. Good night from the graveyard of an unborn world. Good night from 4.5 billion years of patient, quiet, beautiful darkness. Sweet dreams. Now, there is something else about the asteroid belt that I want to spend a little time on before we start winding down. And it is the connection between the belt and the near-Earth asteroid population. Because these two groups are intimately linked, and understanding that link is crucial for understanding the risk that asteroids pose to our planet. Near-Earth asteroids are objects whose Orbits bring them within about 30 million miles of Earth's orbit. There are currently over 30,000 known near-Earth asteroids, and new ones are being discovered almost every day. The vast majority of these objects are small, just a few dozen feet across, and they pose no significant threat. But some are larger, much larger, and a handful are classified as potentially hazardous asteroids, meaning they are both large enough and close enough to Earth's orbit to be considered a potential impact risk. Where do these near-Earth asteroids come from? Most of them originated in the main belt. They were nudged out of their stable belt orbits by one of the mechanisms I described earlier: gravitational interactions with Jupiter, the Yarkovsky effect, or collisions that sent them onto new trajectories. Once an asteroid leaves the belt, it can wander through the inner solar system for millions of years before it either impacts a planet, falls into the sun, or is ejected from the solar system entirely. The average lifetime of a near-Earth asteroid is relatively short by astronomical standards, only about 10 million years. After that, the object is typically removed from the near-Earth population by one of those fates. But the supply is constantly being replenished by new asteroids drifting out of the main belt. It is a conveyor belt of cosmic debris, slowly and steadily feeding objects from the main belt into the inner solar system. This steady supply means that the near-Earth asteroid population is in a kind of dynamic equilibrium. Objects are constantly being added from the belt and constantly being removed by impacts, solar encounters, and ejections. The total number of near-Earth asteroids stays roughly constant over time, even though the individual objects are always changing. Tracking and cataloging these objects is one of the most important tasks in planetary science. NASA's Center for Near-Earth Object Studies, often called CNEOS, maintains a comprehensive database of all known near-Earth asteroids and continuously calculates their future orbits to assess potential impact risks. The Planetary Defense Coordination Office, another NASA organization, is responsible for coordinating the response if a threatening asteroid is ever discovered. These efforts are not just academic exercises. They are practical, real-world applications of the knowledge we have gained from studying the asteroid belt. Every technique we use to track near-Earth asteroids, every model we build to predict their orbits, every strategy we develop for deflecting a threatening object, all of it is built on a foundation of belt asteroid research. The belt is not just a scientific curiosity. It is a laboratory where we develop the tools and knowledge we need to protect our planet. And as our survey capabilities improve, we are finding more and more near-Earth asteroids. The rate of discovery has accelerated dramatically in recent years, thanks to dedicated survey telescopes and improved detection algorithms. The Vera C. Rubin Observatory, currently under construction in Chile, will dramatically increase our ability to detect small near-Earth asteroids when it begins operations. It is expected to find hundreds of thousands of previously unknown objects in the first few years of operation alone. Every one of those objects has a story that begins in the asteroid belt. Every one was once a quiet, unremarkable resident of the region between Mars and Jupiter, orbiting peacefully for billions of years. And then something's happened. A gravitational nudge, a collision, a slow drift caused by the Yarkovsky effect that sent it on a journey inward, toward the warmth of the sun and the orbits of the terrestrial planets. Some of those journeys will end harmlessly. Some will end with the asteroid burning up in a planet's atmosphere or crashing into its surface. And in rare cases, the ending could be catastrophic for any life that happens to be in the way. This is the asteroid belt's most sobering lesson. that the same region of space that delivered water and organic molecules to the early Earth, making life possible, is also the source of the objects that can destroy life. The belt giveth and the belt taketh away. It is both the cradle and the executioner, the source of life's ingredients and the supplier of extinction-level impactors. That duality is fitting because it reflects the duality at the heart of the universe itself. The same forces that create also destroy. The same gravity that builds planets also prevents them. The same collisions that deliver water also excavate craters. Creation and destruction are not opposites in the cosmos. They are the same process, viewed from different angles. And the asteroid belt, sitting quietly in the space between Mars and Jupiter, embodies that truth more perfectly than any other place in the solar system. Actually, before you drift off, let me tell you a few more things, because there is so much about this region of space that I have not even touched on yet, and some of it is too fascinating to leave out. Let me talk about the strangest asteroids in the belt, the ones that do not fit neatly into any category, the ones that make scientists scratch their heads and wonder if they are even looking at the data correctly. There is an asteroid called Pallas. It is the third largest object in the belt, about 318 miles across. Pallas is strange because its orbit is highly inclined compared to most other belt asteroids. While most asteroids orbit the Sun in a relatively flat plane, close to the same plane as the planets, Pallas's orbit is tilted about 34 degrees from that plane. This extreme inclination makes Pallas difficult to visit with spacecraft, because matching its tilted orbit requires a tremendous amount of fuel. It also means that Pallas experiences very different conditions than most belt asteroids, swinging well above and below the main plane of the solar system on each orbit. Scientists believe that Pallas may be a primitive protoplanet, one of the original large bodies that formed early in the solar system's history, but never grew large enough to become a full planet. Like Ceres and Vesta, Pallas is a survivor from the earliest era of planetary formation, a relic of the age when the asteroid belt's building materials were still trying to assemble themselves into something larger. Then there is an asteroid called Hygeia. It is the fourth largest in the belt, about 267 miles across. What makes Hygeia interesting is that recent observations suggest it may actually be round enough to qualify as a dwarf planet, which would make it the smallest dwarf planet in the solar system. The European Southern Observatory's Very Large Telescope captured images of Hygeia that show it has a surprisingly spherical shape, suggesting that it was reshaped by a catastrophic collision in its past. Scientists think that a massive impact shattered the original body of Hygeia into pieces, which then reassembled under their own gravity into the roughly spherical shape we see today. If confirmed as a dwarf planet, Hygeia would join Ceres as the second dwarf planet in the asteroid belt. The idea of an asteroid being completely destroyed and then reassembling itself is one of the most remarkable concepts in planetary science. It is like smashing a vase on the floor and then watching the pieces crawl back together and reform into a vase again, albeit a slightly different one. Gravity is the invisible hand that performs this magic, pulling the scattered fragments back together over millions of years until a new, roughly spherical body emerges from the debris. This process of catastrophic disruption and reaccumulation has likely happened many times in the asteroid belt's history. Many of the rubble pile asteroids we see today may be objects that were shattered and reassembled at some point in their past. They are second-generation asteroids, if you will, Frankensteins stitched together from the fragments of their own predecessors. Let me also tell you about something called the Hungaria group. These are a collection of asteroids that orbit in the innermost region of the belt, even closer to Mars than the main belt population. The Hungarians occupy a relatively stable region of space that is bounded by orbital resonances with Jupiter and Mars. They are like a small exclusive neighborhood on the inner fringe of the belt, separated from the main population by gaps and resonances that act as gravitational barriers. The Hungarians are interesting because they may represent some of the most ancient asteroids in the solar system. Their orbits have been relatively stable for billions of years, and their compositions suggest they are remnants of the original inner disk material that was present when the solar system was forming. Studying the Hungarians could provide insights into the conditions that existed in the very innermost part of the asteroid belt, the region closest to the terrestrial planets, during the earliest era of solar system formation. On the opposite end of the belt, near its outer edge, there is another interesting group called the Cybele asteroids. These orbit beyond the main belt population, in a transition zone between the belt and Jupiter's domain. The Cybeles include a mix of rocky and carbon-rich asteroids, and their orbits are influenced by both Jupiter's gravity and the complex dynamics of the belt's outer boundary. Beyond the Cybeles, there is yet another group called the Hilda asteroids, which orbit in a 3.2 orbital resonance with Jupiter. For every 2 orbits the Hildas complete around the Sun, Jupiter completes 3. This resonance keeps the Hildas in a relatively stable configuration, forming a triangular pattern around the Sun when viewed from above. The Hildas are fascinating because their orbits bring them close to Jupiter at times, giving them a front-row seat to the gas giant's gravitational influence. They are like courtiers in Jupiter's gravitational kingdom, close enough to the throne to feel the king's presence at all times, but stable enough in their positions to avoid being consumed. What makes the Hilda triangle especially beautiful is that it is not a static structure. The individual asteroids move around the triangle, spending time at each vertex in turn. At any given moment, the 3 vertices of the triangle are populated by different asteroids, but the overall triangular shape persists. It is a dynamic pattern, maintained not by any physical connection between the asteroids, but by the invisible mathematics of orbital mechanics. Each asteroid follows its own independent path, yet together they trace out a geometric shape that has persisted for billions of years. It is a silent symphony of gravitational harmony, composed by the laws of physics and performed by rocks that have no idea they are part of something beautiful. And I have not even mentioned the main belt comets. Yes, comets, in the asteroid belt. For a long time, scientists drew a sharp distinction between asteroids and comets. Asteroids were rocky objects in the inner solar system. Comets were icy objects from the outer solar system that developed tails when they approached the Sun. The two were considered completely separate populations with completely different origins. But in recent years, that distinction has become blurred. Scientists have discovered objects in the asteroid belt that exhibit comet-like behavior. They develop tails, or more accurately, they emit jets of gas and dust, just like comets do. These are called main belt comets, or sometimes active asteroids, and their existence suggests that there is more ice in the asteroid belt than scientists previously thought. The first main belt comet was discovered in 1996. An asteroid called 133P Elst Pizarro was observed to have a dust tail, like a comet. At first, scientists were skeptical. Maybe it was just a comet that had wandered into the belt from the outer solar system. But subsequent observations confirmed that Elst Pizarro was a genuine member of the asteroid belt, orbiting in the main belt for billions of years, not a visitor from the outer solar system. It just happened to contain enough ice beneath its surface that when sunlight warmed it sufficiently, the ice sublimated and produced a visible outgassing event. Since then, several more main belt comets have been discovered. Their existence is important for multiple reasons. First, they confirm that water ice exists within the asteroid belt itself, not just in the form of hydrated minerals, but as actual ice. Second, they suggest that the delivery of water to the early Earth by belt asteroids may have been even more efficient than previously thought, since some of those asteroids contain not just chemically bound water, but free ice as well. And third, they blur the boundary between asteroids and comets, suggesting that these two populations are not as distinct as we once believed. The solar system is messier and more complicated than our neat categories suggest. Let me tell you one more thing about the physical conditions in the asteroid belt, because I think it helps complete the picture of what this region is actually like. Temperature in the belt varies significantly depending on distance from the Sun, and whether a particular spot on an asteroid's surface is in sunlight or shadow. In direct sunlight, at the distance of the inner belt, surface temperatures can reach about minus 70 degrees Fahrenheit. That sounds cold, and it is, but it is warmer than you might expect for something so far from the Sun. The key word is indirect sunlight. The moment a spot on an asteroid rotates into shadow, the temperature plummets. In shadow, temperatures can drop to minus 200 degrees Fahrenheit, or even lower. There is no atmosphere to retain heat, no blanket of air to moderate the temperature swings. The transition from sunlight to shadow is a transition from merely cold to desperately, bitterly cold. In the outer belt, further from the Sun, both the sunlit and shadowed temperatures are even lower. Surface temperatures on C-type asteroids in the outer belt can drop to minus 240 degrees Fahrenheit in shadow. At these temperatures, even carbon dioxide is a solid. Water is as hard as granite, and any exposed ice will sublimate, transitioning directly from solid to gas at an incredibly slow rate, preserving it for billions of years. The radiation environment in the belt is also harsh. Without an atmosphere or magnetic field to provide protection, asteroid surfaces are exposed to the full force of the solar wind and cosmic radiation. Charged particles from the Sun constantly bombard the surfaces of asteroids, gradually altering their chemistry and darkening their appearance through a process called space weathering. This is why asteroid surfaces tend to be darker and redder than the fresh rock beneath. The constant bombardment of radiation chemically alters the top layer. Cosmic rays, high-energy particles from outside the solar system, penetrate even deeper. They can reach several feet below an asteroid's surface, breaking apart molecules and creating new chemical compounds. Over billions of years, this radiation processing can significantly alter the chemistry of an asteroid's outer layer. This is one of the reasons why scientists are so eager to collect samples from below an asteroid's surface, where the material has been shielded from radiation and is more representative of the asteroid's original composition. These harsh conditions, the extreme cold, the radiation, the vacuum, make the asteroid belt one of the most inhospitable environments in the solar system from a human perspective. And yet, there is something appealing about that harshness. It is honest. The belt does not pretend to be welcoming. It does not lure you in with false promises. It is what it is: cold, dark, silent, and enduring. And in that brutal honesty, there is a kind of beauty. The asteroids do not need warmth or light or sound to exist. They do not need observers or admirers. They are complete in themselves, self-sufficient in a way that nothing on Earth can ever be. They have no needs, no desires, no fears. They simply orbit and spin and exist in the most basic and profound sense of that word. And in our busy, noisy, anxious world, there is something deeply calming about contemplating objects that exist without anxiety, without urgency, without the relentless drive to grow, to change, to become something more than what they are. The asteroids are perfectly content to be exactly what they are, rocks in space, and they have been content with that for longer than life has existed on Earth. That contentment, that absolute acceptance of what is perhaps the most valuable lesson the asteroid belt has to offer. Not a scientific lesson, but a philosophical one. A reminder that existence does not require justification, that being does not require purpose, that you can simply be, quietly and patiently, for as long as the universe allows, just like an asteroid floating through the dark, silent belt between Mars and Jupiter. So let that thought carry you into sleep. Let the quiet patience of the asteroid belt seep into your mind. Let the vast, empty darkness wrap around you like the softest blanket. And know that somewhere out there, between the fourth planet and the fifth, millions of ancient rocks are floating through the same darkness, keeping you silent company, just as they have since before your planet was formed. The cosmos is vast, and you are small, and the asteroid belt is mostly nothing. But within that nothing, there is everything. The story of our origins, the ingredients for our existence, the ruins of an unborn world, and the quiet, patient promise that no matter how chaotic things get down here, on Earth, the belt will still be there, still orbiting, still spinning, still waiting, always waiting. But actually, there is one more thing I want to share with you before the silence takes over completely. Because I realized I have not told you about one of the most mind-bending aspects of the asteroid belt, and it has to do with what happens when you look at it not as a collection of individual objects, but as a system, a single, interconnected, dynamic system. See, the asteroids in the belt are not truly independent of each other. They influence each other gravitationally, even across the vast distances that separate them. When a large asteroid passes near a smaller one, it gives it a tiny gravitational tug. That tug changes the smaller asteroid's orbit by an imperceptible amount. But over millions of years, those tiny tugs add up. And the cumulative effect of millions of asteroids tugging on each other over billions of years creates a complex, chaotic system that is almost impossible to predict in detail. This is called gravitational chaos, and it is one of the reasons why the long-term behavior of individual asteroids is so hard to forecast. You can predict an asteroid's orbit with extreme precision for a few thousand years into the future. But beyond that, the accumulated uncertainties from all those tiny gravitational interactions make the prediction increasingly unreliable. After a few million years, you essentially lose all ability to predict where a specific asteroid will be. The system is deterministic in principle, but unpredictable in practice. This chaotic behavior is not unique to the asteroid belt. It is a fundamental property of systems, with many interacting bodies. Even the orbits of the planets in our solar system are chaotic on long enough timescales. But in the asteroid belt, with its millions of interacting objects, the chaos is particularly pronounced. It is one of the factors that drives the slow evolution of the belt, constantly reshuffling orbits, creating new collision possibilities, and occasionally sending an asteroid onto a path that takes it out of the belt entirely. There is something almost alive about this behavior. The belt is not static. It is breathing, shifting, evolving, slowly, imperceptibly, but constantly. Each asteroid is part of a vast interconnected web of gravitational influences, and each one's fate depends on the cumulative pull of all the others. It is a system that is greater than the sum of its parts, a collective that exhibits behavior that no individual asteroid could produce on its own. This systemic perspective also helps us understand why the Kirkwood gaps I mentioned earlier are so sharp and well defined. You might think that because individual asteroid orbits are chaotic, the gaps would be fuzzy and indistinct, but the opposite is true. The resonances with Jupiter that create the gaps are so strong that they dominate the chaotic background. Any asteroid that wanders into a Kirkwood gap is quickly ejected by the resonant gravitational pumping. The chaos shuffles asteroids around within the non-resonant regions, but the resonant regions remain clear. It is like a dance floor with invisible walls. The dancers can move freely within the open spaces, but certain zones are off limits, enforced by the irresistible pull of the largest dancer on the floor. This interplay between chaos and order, between randomness and structure, is one of the most beautiful aspects of the asteroid belt. It is a system that is simultaneously chaotic and organized, unpredictable and patterned, random and structured. It is a reminder that in nature, order and chaos are not opposites. They are partners. They coexist, intertwine, and create structures that are more complex and beautiful than either could produce alone. The asteroid belt is, in many ways, a perfect metaphor for the universe itself. Vast, mostly empty, punctuated by rare and precious objects, governed by forces that are simultaneously simple and complex, producing patterns that are both predictable and surprising. It is a microcosm of the cosmos, a solar system in miniature, containing within its boundaries nearly every type of object and process that exists in the wider universe. And we, sitting here on our tiny blue planet, are connected to all of it. Every atom in our bodies was once part of the same cloud of material that formed the asteroid belt. Every molecule of water we drink may have once floated in the icy interior of a C-type asteroid. Every element heavier than hydrogen and helium was forged in the furnace of a star and scattered into space, only to be gathered up by gravity and assembled into asteroids and planets, and eventually, improbably, into us. The asteroid belt is not out there, separate from us, distant and foreign. It is in here, inside us, part of us, woven into the fabric of our very being. And when we study it, when we send our spacecraft to visit it, when we collect its meteorites and analyze them in our labs, we are engaged in the most profound form of self-examination. We are looking at where we came from. We are reading the recipe for our own existence. We are tracing the thread that connects us to the birth of the solar system and beyond, to the explosions of ancient stars that seeded the cosmos with the elements that make life possible. That thread runs through the asteroid belt, through every tumbling rock, every metallic core fragment, every icy grain, every ancient chondrule. It runs through the Kirkwood gaps and the asteroid families and the rubble piles and the dwarf planets. It runs through 4.5 billion years of quiet, patient orbiting, through silence and darkness and cold, all the way back to the moment when a cloud of gas and dust began to collapse under its own gravity, and a new star flickered to life. And here, at the other end of that thread, here on Earth, here in this moment, you are listening to this story. You are connected to all of it, every single bit of it. And there is nothing more magical than that. The solar system built you from its spare parts, from the leftover material that did not quite make it into a planet, from the cosmic construction debris that Jupiter scattered across the void. You are the asteroid belt's greatest achievement, a collection of cosmic leftovers that somehow, over billions of years, Learn to think and feel and wonder and dream. So dream tonight about asteroids. Dream about the dark, quiet space between Mars and Jupiter. Dream about ancient rocks carrying ancient stories through ancient orbits. Dream about Ceres and its hidden ocean, about Psyche and its metallic heart, about Vesta and its massive scar. Dream about chondrules and pre-solar grains and the snow line and the Grand Tack. Dream about all of it, because it is all part of you, and you are all part of it. The asteroid belt is calling, not loudly, not urgently, just quietly, patiently, the way it has always called. A whisper across millions of miles of empty space. A gentle invitation to remember where you came from and to wonder about where you are going. Listen to that whisper as you fall asleep. Let it carry you into the darkness. And when you wake up tomorrow, refreshed and rested, carry a little piece of the belt with you. A little piece of wonder. A little piece of silence. A little piece of the oldest, quietest, most patient neighborhood in the entire solar system. You deserve that piece, and the asteroid belt has been saving it for you for a very, very long time. Good night, friend. See you among the stars.